Well, chapters 22 and 23 together comprise some of the scariest parts of organic chemistry, because we're going to be doing syntheses that wind up making molecules that look darn near nothing like what we start with. Okay? But the basic principle for all of these reactions is going to be the same. And if you can hold down the panic attack and simply look at it, ask yourself a few questions as you go, it's actually quite doable. It really is. Generally, these are going to be called carbonyl alpha substitution and condensation reactions. This all comes down to a concept that we talked about way back in chapter 17. We said that carbonyl compounds, specifically we're talking about ketone and aldehydes, exist in equilibrium with what's known as an enol. The process is called Tautomerism. It's not a resonance form, therefore it's two arrows. We are changing hybridizations. We are actually physically moving protons. But ketones and aldehydes are always in equilibrium with their enol. Now the enol is a very, very small fraction of a ketone or aldehyde at equilibrium, usually. If we have cyclohexanone, 99.999% is going to be present as the ketone, and only a tiny bit here as the enol. Nonetheless, enols have the ability to impart real reactivity to the alpha carbon of a ketone or aldehyde. The isomerism from a ketone to an enol can be described as a simple acid-base equilibrium. If we have a base, pulling up a proton, we're going to make BH here. And here's our base that we started with. This allows us to talk about the pKa, that is how acidic this particular carbon atom is. From general chemistry, products over reactants, equilibrium constant about 10 to the minus 19. Now once again, that tells you there isn't much of this at equilibrium, is there? pKa of about 19 or 20 is typical for an aldehyde or a ketone. This is the concept of what we call carbon acidity. Carbon compounds in general are very, very weak acids. If you start down here with something like methane, the pKa of the hydrogens on ethane is about 60. Really, really, really basic. If we put electron withdrawing groups on here we have a carbonyl, an ester group. These CHs drop down to in the 20s. We just did ketones at about 19. Chlorine is more electron withdrawing, therefore this drops to about 16 or so. Nitriles are very nicely electron withdrawing. And this guy up here wins. This is pentane, 1, 2, 3, 4, 5, 2,4-pentane dione. For a carbon compound, it has a remarkably low pKa of about 9. Now, why is that? It's because we have two carbonyls that are beta, I'm sorry, beta to each other. Remember this, the alpha position, that's the beta. And these exist as these resonance hybrids. This is the hybrid here. And we totally disperse the negative charge over the two carbonyl oxygens, and of course there's some charge also on the central carbon. We will use the acidity of this central carbon as a nucleophile. Whenever you have beta dicarbonyls, you will have a very nicely acidic hydrogen in between. One of the key things. Just use your intuition here. Look at this selection. See if you can pick out the strongest carbon acid and the weakest. Well, as we look at these, this is benzene. If we have a negative charge here, there's no place for it to go, is there? It's just a plain, naked carbanion. Here we have a ketal, actually, or acetal. The carbons here in the middle are going to be the acidic ones, and they're acidic because we have electronegative oxygens on both sides. These are acidic, aided by the carbonyl and the trifluoro group. Here, just the carbonyl. And this guy is a 1,3 beta carbonyl, dicarbonyl. This guy is going to be the most acidic, and the least acidic is going to be up here, just plain old ugly benzene. This is actually the ordering. Benzene, once again, is around 60, and this diester is about 13. So remarkably acidic for a carbon compound. Now what we're going to do today is use the acidity of these alpha carbonyl hydrogens. We're going to generate a carbanion at that point and use that as a nucleophile. One of the examples we're going to do. Here we have a cyclopentanone with a methyl group in carbon 2. We will see that we can take this, because this has an enol character at the alpha carbon, we can convert this into something like a bromo carbonyl. Why do we want to do that? If we have an alpha bromo carbonyl compound, this can undergo a very simple E2 elimination and give us an alpha beta unsaturated carbonyl. Why do we care about that? Remember, we talked about the Michael reaction. We can add things here, can't we? Add it to the beta carbon. We can also do all the chemistry associated with a double bond. So this gives us an end to doing lots and lots of chemistry on fairly simple compounds. Let's see how this works. Here we have acetophenone, plain old happy carbonyl. If we take acetophenone and we dump it in acetic acid and add some bromine. So acetic acid is our solvent, add some bromine. The conversion from an enol to the carbonyl is both catalyzed by acid and base, because you have to donate a proton and remove a proton. So the acid catalyzes the enolization. Our product here is the alpha bromo compound. The first step, the acid simply catalyzes enolization to give us the appropriate acetophenone enol. Now, whenever you have an enol, remember we can remove this hydrogen, put the electrons down, and we will generate negative character at the alpha carbon. This potential carbanion is the nucleophile that we're going to use. So the acid catalyzes the enolization. As it collapses, we form the carbanion here. The carbanion simply attacks bromine, and we wind up with the alpha-bromo compound. Very, very simple. Works very nicely for both aldehydes and ketones. Any questions? Well, let's do a couple. Quickly jot down the products of these alpha-bromo carbonyl reactions. Cyclohexanone and acetic acid with a touch of bromine added. We are going to form the enol between the alpha and the beta carbons. That will give us negative character on the beta carbon here. I'm sorry, the alpha carbon here. And we will form the alpha-bromo carbonyl. You can also do this with chlorine. Chlorine. Here we use aqueous HCl instead of acetic acid because you need a stronger acid for this. Again, we're going to protonate the carbonyl carbon. The enol character will give a carbanion here on the CH2 group that will attack Cl2, and we will make the alpha-chloroaldehyde. And our last guy here, we have a methyl cyclohexanone. Again, we have acetic acid, we have bromine. We are going to put negative character on this carbon adjacent to the carbonyl. It will attack bromine, and it will give us the alpha-bromo compound. Now, it will be very correct of you to point out at this point that, hey, we have two non-equivalent groups here. Why do we put it here? Well, remember, way back in 234, we did Cis-Neff's rule. What do you know about forming alkenes? You want the most highly substituted alkene. So this is the most highly substituted enol to give this product. This product is really not observed. Cis-Neff's rule. Any questions? Now there's one particular halogenation reaction that is very notable when it comes to aldehydes and ketones. And this is called the iodoform reaction. If you take a methyl ketone or a methyl aldehyde in the presence of base and iodine, well, we can pretty much figure out what's going to happen. Base catalyzed enolization. Okay, we can do that. Once we do this, we will put negative character here, like this. We have iodine in the pot. Not surprisingly, this is going to attack iodine, and we will make the alpha iodo aldehyde or ketone. Right? However, we still have base, we still have iodine, and actually this compound is now more reactive than this one. And so this is going to react with another mole of base to make a different enol, one with the iodine on it. This is going to make negative character down here, react with another mole, and give us the diiodo, which is even more reactive. This is going to do it a third time, down here to the triiodo methyl ketone or aldehyde. Now nothing else can happen, but the triiodo ketone, this guy, the triiodo methyl group, is actually a decent leaving group because these are electronegative enough that they can suck up the negative charge. So what happens is this stuff reacts with base. We get a tetrahedral intermediate, remember that. And this is our leaving group, iodoform. Iodoform is a bright yellow stuff. This is used in qualitative organic chemistry. Let's say you have a compound that you think might be a methyl ketone. You want to test. Put it in base, add a little bit of iodine, boom, you get this precipitate right away of iodoform. Now the same thing happens with chlorine and bromine, but chloroform and bromoform aren't that interesting. Iodoform really is good. The bottom line thing to remember here is that the iodoform test diagnoses a methyl ketone or aldehyde. Very, very useful. Quite often this shows up on standardized exams. Any questions? Now we know that we can make alpha iodocarbonyls other ways. The direct bromination that we did with aldehydes and ketones with just bromine, acetic acid, doesn't work with other acyl compounds. However, we can do the Hell-Volhard-Zelinskii. Cover this in chapter 20, I believe. Very simple. We have bromine, PBr3, and water. Remember the steps. PBr3 reacts with the carboxylic acid to make an acyl bromide. Acyl bromide enolizes, reacts with bromine, dump in water, and we wind up with the carboxylic acid. Just to make sure you were paying attention to what I said, quickly draw the steps out for this particular reaction. Step 1, you want to make the acyl bromide. Step 2, you want it to enolize. Step 3, the enolate anion attacks bromine to give the alpha-bromo acyl bromide. And just to make this interesting, instead of dumping it in water, I'm putting it in 2-propanol. So 2-propanol will react with the acyl bromide. Step one, make the acyl bromide, that's the acid plus PPR3 acyl bromide. Nice and reactive. Step two, acyl bromide is going to enolize. Nice electron withdrawing group here, acidifies these even more, and we make the enolate that looks like this. Whenever you have an enolate, remember, we're going to have negative charge at the alpha carbon. So these electrons will move in, they will then attack Br2, and we make the alpha bromo acyl bromide. Finally, when you have an acyl bromide, acyl chloride, whatever, in the presence of an alcohol, the alcohol will simply attack the carbonyl, bromine will leave, and we will make the ester. If the lab last week would have worked, or was it Tuesday? If it would have worked, we would have an acyl chloride reacting with ammonia. Same chemistry. Didn't work. Not my fault. Any questions? Like I said, one of the neat things about doing the alpha bromination reactions is that we can convert these into alpha beta unsaturated carbonyl compounds. The mechanism is very simple. Base simply attacks the beta carbon here, pulls out hydrogen, bromine leaves, E2 elimination. These two must be interfacial and coplanar, and we get the alpha beta compound. Very quickly, just jot down the products for these very simple eliminations. I've used pyridine here as a solvent. Pyridine, recall, is a heterocyclic nitrogen compound. It's a base. It works very nicely for these elimination reactions. Remember, all we're going to do here is simply eliminate HBr. We're going to form, according to Zaitsev, the most highly substituted alkene, right? 234, remember that. That means we're not going to eliminate across the methyl group here, are we? Although we could. We're not. We're going to eliminate this way to get a tri-substituted alkene. Here with alpha bromo cyclohexanone, the elimination is going to go this way. We're simply going to pull that off and make cyclohexenone. Any questions? There are other more elegant ways to make alpha beta unsaturated carbonyls. Probably one of the smelliest is this. You can take a carbonyl compound. We'll talk a little more about this, but this is just a simple ketone. if you treat it with a very, very strong base. Now this is disopropyl lithium amide, okay? This nitrogen has a pKa of about 45. Really, really basic. It can react with a carbonyl compound to form a stable enolate anion. In this case, we could pull off hydrogens from the methyl or from the CH2. Side-steps rule says we're going to do the CH2, and we're going to get the lithium enolate. Now we're going to use this particular reaction again. So kind of remember it. Lithium, LDA is called, lithium disopropyl amide. Simply pull off the hydrogen and make the enolate as a stable thing. In this particular reaction, next we're going to react this with benzene selenilyl bromide, this stuff. The selenium can undergo an SN2 attack by the enolate anion here. Bromine leaves, and we get this selenium atom. Now, once we're here, selenium, just like sulfur, if we had a periodic table, we could see how close they were to each other. But selenium is just under sulfur, and they both react with peroxide to form oxidants, so you put two oxygens here on the selenium. That makes it an excellent leaving group. So if we take this stuff, dump in hydrogen peroxide, this becomes a super leaving group, boom, it's gone, and we make the alpha beta unsaturated compound. This type of chemistry is something that you would do, kind of like using diazomethane. Remember I said you save that for the stuff that you worked years to make, right? Because it's so dangerous. This isn't dangerous, but my God, does it stink. It is so bad. It is so much worse than thiol compounds. It really is bad stuff. But you don't do this unless you're making a very precious alpha beta unsaturated carbonyl. The yield is very good though. Any questions? Let's go ahead and do some simple reactions here. This is just the elimination. You'll see that this chemistry not only works with simple aldehydes and ketones, but also applies to esters, nitriles, and again, here, just a simple ketone. So what you're doing here, step one, you're going to look and identify the carbon that's going to form the enolate anion. That is going to react with the selenium. Then the beta carbon, when we do the peroxide workup, is going to lose the hydrogen, you lose the selenium, and you make your alkyl. So in our first one, our alpha carbon is the tertiary carbon here next to the carbonyl. So that's where we stick the selenium. Step two, we're going to pull off a hydrogen from down here, and we will make the alpha beta unsaturated ester. With our nitrile, this is the alpha carbon. This is where we will have carbanion character once we form the enolate. Now, it's not really an enolate. It's the nitrile version. We'll see a picture of that in a minute. We will attack the selenium at this carbon, remove a hydrogen here, and we will make the alpha-beta unsaturated nitrile. And finally, this guy. LDA is going to give us the enolate anion. We're going to attack the selenium, going to do our oxidation, and we will make the alpha-beta unsaturated cis-F alkene. Any question? I hope by now that the key thing is starting to sink in. The key point of all of this is that we're going to form an enolate with carbanion character on the alpha carbon, and then we're going to do things with it. We did it with bromine. Here we've attacked selenium with it. I'm sure you're sitting here asking yourself, gee, can you use this in a simple SN2 reaction? I'm sure you're saying that to yourself, right? Of course you can. If we take acetophenone, we can take something like bromomethane and simply stick a methyl group here on the alpha carbon. Isn't that amazing? Now, how do we do that? Step one, we have to make the enol. The enol is going to have carbanion character here at the alpha carbon. And this carbanion is simply going to attack the methyl. All of a sudden, here we are. What do we need to promote this reaction? Well, it depends on the carbonyl compound you're dealing with. Enolization is both acid and base catalyzed. But this reaction, if you just dumped it in acetic acid, wouldn't work very well. With something like this, you want to cheat a little bit. And this is where we're going to cheat and use LDA again. Remember, LDA is strong enough as a base to pull this off and make a stable lithium enolate. Now, because of the tautomerization, we still have negative charge down here, don't we? So if we take this, dump in an alkyl halide of some sort, the carbanion at this point can attack, and we have alkylated our alpha carbon. We will see other examples where we can do this without using LDA. But LDA is a nice old way to do it. You convert it totally to the enolate, dump in your alkyl halide, and boom, you've got your product. Let's do some examples. We've already seen that we can do LDA with esters, nitriles, and simple carbonyls, right? Same chemistry over and over again, my friend. All right, our first one, LDA is going to make the enolate of this ester, and the negative charge will be here on the alpha carbon. That will attack bromomethane, and that will be our final product. And our second one, the carbon adjacent to the nitrile is the one that's acidic. The carbanion will be at this carbon. It will attack bromomethane, and we will make the methylated product. And finally, here we have a methyl cyclohexanone. Now, everything that we know tells us that this is going to be the enolate anion carbon, and it should be. However, the product we get is actually this one, because the geometry of the six-membered ring is such that doing a substitution here is unfavorable. It's just too crowded. So we actually wind up with the unexpected product. You wouldn't have to know that. Any questions? All right, let's summarize what we know about alpha substitution. We can take a carbonyl compound. We can convert it to an enolate. We can add something like an alkyl halide or a bromine, and we can form an alpha substitution like this. Again, this is the carbon backbone where we started, and we've simply added a chunk. It works with ketones, aldehydes, esters, nitriles. Nice, simple reaction. Any questions? All right, do a synthesis for me then. We're going to start off with acetaldehyde, that's FNL. And we're going to make 1, 2, 3, 4 butanal. Now, obviously, we have tacked something on to the alpha carbon, haven't we? That's the real trick of all of this, is to figure out what you have tacked on. Identify the carbons that used to be ethanol. This is ethanol, these two carbons here, right? So what did we stick on? We stuck on a 2-carbon chunk. Now, how do we do that? We make the ethanol enolate, and we'll react it with an alkyl halide. Here's our enolate anion. This 2-carbon chunk is our alkyl halide. This alpha carbon attacks, bromine leaves, and we get our product. We can do this with LDA, THF, simply followed by bromoethane. Any questions? To figure out the carbons that belong to your starting material, and you figure out what else you had to add. We can do that. All right, let's do one more. Again, let's start with acetaldehyde. And here we want to make beta hydroxy. Well, that's 1, 2, 3. 3-hydroxy butanol. Now do this exactly like we did the other one. Figure out the carbons that came from ethanol. Draw your little squiggly line and see what's on the other side. Well, there's our line. Well, the carbons on this side are ethanol. What's on the other side? This is a CH, an OH, and a CH3. It's a secondary alcohol. Huh. How do we do that? Well, we could have done it simply by taking our enolate anion, and this carbon has to attack something that's going to give us an OH, hydrogen, and a methyl group. What is that? Why, it's another mole of ethanol. The carbanion simply attacks, picks up a hydrogen, just like a Grignard reagent would attack, right? Therefore, because this came from ethanol and this is ethanol, we simply need 2 moles of it in the presence of base. This, my friends, is the aldol condensation, one of the hallmark reactions of organic chemistry. This compound here is called aldol. It is, again, one of the important reactions in all of organic and even biochemistry. 2 moles of an aldehyde or a ketone, presence of base, enolate, attack, beta hydroxy carbonyl. Go ahead, take this stuff. This is 1, 2, 3, 4. This is 3-methylbutanol. Do an aldol condensation on 3-methylbutanol. Step 1, you want to write the structure of the enolate anion. Step 2, you want to take the alpha carbon and attack the carbonyl of another mole of this stuff. So step 1, we're going to enolize. Here's our butanol, and there's the enol. The alpha carbon is going to attack the carbonyl of the next guy. This is going to be our hydroxyl group. We're going to be bonded through the alpha carbon, and the product will look like this. This half here, right here, this is the bond that we just made. So this half is 1 mole of butanol, used to be a carbonyl. This is the other mole of butanol, methylbutanol. Make sure you can look and see that. With the alpha carbon and attack, here's the alpha carbon. We've made this bond. This is now the OH. It's a beta hydroxy aldehyde. Let's do this again. Just take plain old cyclohexanone. Dump it in base, and let's see what happens. Draw the enolate anion. Take the enolate anion, attack with the alpha carbon on this carbonyl of another mole, put a hydrogen on it, here's our second mole of cyclohexanone. Here's our enolate anion. The alpha carbon will attack the carbonyl, and this will become an OH. Pick out the proton. And that's our product. This is one cyclohexanone, and this is the other. I have spoken of biochemistry several times, and I've talked about biochemistry being taught by an organic chemist versus a biologist. I'm sure you've all heard of glycolysis. There's an enzyme in there called aldolase. Now you understand the name aldolase, right? Aldolase catalyzes a reverse aldol condensation. This is dihydroxyacetone. Dihydroxyacetone has this unique ability to turn your skin an ugly brown. It's what they use in tanning sprays. Okay. Biologically, this exists as dihydroxyacetone phosphate, and we're going to react that with glyceraldehyde 3-phosphate. What we're going to do is simply take an enolate anion, attack a carbonyl, and we will make fructose. This is the way it works. The dihydroxyacetone phosphate reacts with the amino group of a lysine side chain and forms an imine. This holds it down, number one. Plus, the ammonium ion is very good at acidifying the alpha hydrogen because it's positive. So this is now going to form an enolate. This enolate right here is going to have negative character. It's going to react with glyceraldehyde 3-phosphate, going to attack the carbonyl, and we're going to form this stuff. Now there's our imine still holding it to the enzyme. Now the enzyme will hydrolyze the imine, converting it back to a ketone. This is the bond we just made. So now it's a ketone again, been released from the enzyme. And here, 5 centers away, we have an OH and a carbonyl. This simply attacks, and we form fructose 1,6 bisphosphate. Glycolysis typically runs in this direction, so aldolase catalyzes a reverse aldol condensation. Isn't that simple? Isn't that neat? Yeah.
For this compound here, did you take another second mole to form this side of the chain?
No, this is the dihydroxyacetone phosphate. This is the glyceraldehyde phosphate. Simply link them together. That's the bond you made.
I'm talking about that second O3P.
Oh, here?
No, right.
Oh, this guy?
No, up here.
Up here. No, this is dihydroxyacetone.
No, right here.
Here.
On this third thing you've got.
This guy.
That second O3PO. Yeah, that's
Oh, no, here's our CH2. So here's the bond we made.
But
yeah.
where did that chain come from?
This is half of this and half of that.
Okay.
Split right down the middle. 3 carbons each, 6 carbons total. Don't you wish you would have figured this out? They were just darn good chemists back in those days. All right, one of the neat things about making beta-hydroxycarbonyls, once again, is that you can get rid of the hydroxy group. And it's so easy, you typically do it by accident. If you just take a beta-hydroxycarbonyl and show it a little bit of strong acid, you'll protonate this. Again, we have an E2 elimination, and we're here at the alpha-beta unsaturated carbonyl. Let's do some examples. Take these aldol condensation products and simply do a dehydration. Remember, all we're going to do is remove a proton from the alpha hydrogen. The OH group is going to leave as water. Going to make a double bond through here. And that's our product. Our second aldol adduct. We're going to remove the alpha hydrogen here, remove the OH group as water. And here's our cyclohexanol adduct. We're going to remove the alpha hydrogen, remove the OH as water, and make the exocyclic alkene. Any questions? All right, let's do one backwards. Here we have some compound. It was made by an aldol synthesis followed by dehydration. You need to tell me the aldehyde that was used for this reaction. Now this is actually really simple. You look at it and say, this is an alpha-beta unsaturated compound. So there used to be an OH group here, didn't there? Used to be one. So simply draw the structure of the beta hydroxyaldehyde. And all that is this guy with an OH group at the beta carbon. And there we go. Now we can do this pretty simply, can't we? We know that the alpha carbon of one aldehyde attacked the carbonyl of another. So the bond that we made was this guy. So this half is one aldehyde, this half is the other. Therefore, our enolate must have looked like this. The aldehyde looked like this. The enolate anion attacked to give us this adduct. And our aldehyde, simply 2 moles of butanol. Now, there are lots of tricks you can do with an aldol condensation. Let's look at this guy. Here we have a diol. 1, 2, 3, 4, 5, 6. It's a 2,4-hexane diol. If we treat this with base, and do an internal aldol condensation, what would we get? Well, this is the structure. This is after dehydration. And I hope you're puzzling to yourself and saying, what? How'd that happen? Well, it's actually really simple. Let's go ahead and do this stepwise, okay? Let's form an enolate. Now, we know that the predominant enolate that we're going to form is going to be at this carbon, because that's the side-step rule. But sometimes it's nice to break the rules. And we will also have enolate character on this methyl group. Okay? Now, I'm going to take this and wrap it around itself a little differently. So it looks like this. Just redrawing, same thing. Now I hope you can see that this enolate anion is all set up to attack this carbonyl which is 5 centers away. What's going to happen is the enolate will collapse, the electrons will attack, and by George, we make the beta hydroxy ketone. Now you see, if we had had enolate character here, and it tried to attack, that would be a 3-membered ring. That's not going to work, is it? But here, a 5-membered ring, that's happy. That's what drives this reaction. Now all we have to do is acidify this a little bit, and by George, we have the alpha-beta unsaturated carbonyl. Lots of interesting molecules can be made using internal aldol condensations. All right, so here's our second thing of our bottom line. Enolates from aldehydes and ketones add to the carbonyl of a second mole to get beta hydroxy ketones and aldehydes, which can be dehydrated. Any questions? Well, let's return just a moment here to our alpha-beta unsaturated carbonyl. We've seen these. We saw them back in chapter something or other. I don't know what it was, but we saw it before, right? I know we did. We looked at the alpha-beta unsaturated group, and we drew an analogy between it and the 1,2 and 1,4 addition of diamonds. That is, our alpha and our beta carbons here. We can form this carbocation, which is stabilized this way. This is our enolate anion as a zwitterion, the oxyanion and the carbocation. We said that we could use a nucleophile and attack this carbocation character at either the 2 position or the 4. If we attack it at the 4 position, we get this sort of adduct nucleophile attached to our beta carbon. Very useful reaction is called the Michael reaction. Now what we did so far, we looked at diethyl aluminum nitrile. We said that the nitrile group can add to the beta carbon. We looked at dialkyl copper lithiums. We said that the alkyl group also adds to the beta carbon. And we looked at simple amines. The nitrogen also adds to the beta carbon. And we get an array of compounds like this. Now, I'm sure you are sitting back and saying to yourself, hey, I wonder, can we add an enolate anion to the beta carbon? Well, of course we can. Let's take our pentane dione enolate anion, simply add the enolate anion carbon to our beta position, and wow, look at what we've just made. See how we can build up molecules very quickly of great complexity. All we've done is add the alpha carbon to the beta carbon of our unsaturated carbonyl. Let's just do a couple. I have dimethyl malonate. That's going to come back. We're going to see malonate ester reactions. Just like any beta diketone, the central carbon here is very acidic. pKa of 9 or 10. It's going to attack the beta carbon. Go ahead and draw the structure. All you need is a bond from here to here. A bond from here to here. This is the bond we just made right here. From here to here. Now our next guy is called malonitrile. It's the same oxidation state on both carbons as malonic acid. Again, this is a very acidic carbon. Our band ion will attack the beta carbon. Go ahead and draw it. You can do this. This is an art class. All you need is a bond from here to here. This is the bond we just made. I'm sorry, this is the bond we just made. This was our alpha beta unsaturated ketone. And our last guy will also come back to haunt us in just a few moments. This is called methyl acetoacetate. Again, a beta dicarbonyl. Similar to this, we have ester on one side, methyl on the other. Very acidic. It's going to attack here to here. Draw your product. All we do is draw our bond, once again, from the central carbon here to the beta carbon, and it looks like that. Really nice, complex molecules, aren't they? Well, let me talk a little bit more here about our first guy here, a malonic acid diester. This has really unique properties. Like I said, this carbon is nicely acidic. So if we take something like diethyl malonate, we could just put in ethoxide. Remember the pKa here is 9 or 10, right? Ethoxide, the pKa is 16. So it's a much stronger base. It can pull this off just like LDA would, or a ketone, and make pure enolate anion. That's kind of neat, okay? Now, what in the world are we going to do with this enolate anion? Well, we know we can do all sorts of stuff, right? You can use it as a nucleophile towards anything. How about if we did this with an alkyl halide? What if I took Rx, took the enolate anion, attacked it, I would make a substituted diethylmelanate. Okay, that's kind of cute. Now, diethylmelanate is an ester, right? We know that Fischer esterification, acid and water, is in equilibrium. If we took this sucker and we dropped it into aqueous acid, what would happen? We would hydrolyze these esters. Here we go. We've alkylated it, and now we just hydrolyze the esters. Oh my goodness, look at this. Remember in our chapter on carboxylic acids, we talked about beta diacids? What do? Oh my goodness, they decarboxylate. And when they do, we're left with an enol again. But this is going to collapse quickly, and it makes a substituted acetic acid. Now think about what we've done. We've taken diethylmelanate. We stuck on anything we want here that we can do with an SN2 reaction. Anything. Dump it in acid, decarboxylates. Now here's our R group attached to a CH2 and a carboxylic acid. This chunk here, the CH2 and the acid, is our acetic acid derivative, and here's the R that we've stuck on. This is called a malonic ester synthesis. You should write this down. The hallmark of a malonic acid synthesis, malonic ester synthesis, is that we make a substituted acetic acid. Malonic ester synthesis yields a substituted acetic acid. All right, so let's do this backwards then. Here I have a carboxylic acid. We have an alkene dangling out on the end. It's a 3-butanoic acid. And I made this using a malonic ester synthesis. How in the world did I do that? Step one, you look at your molecule and identify the acetic acid portion. That's what used to be the diethylmelanate. So identify the acetic acid portion. In this case, it's the CH2 and the carboxylic acid. So what did we add? We added a CH2 and a double bond. How did we add it? With an SN2 reaction. All right, so what did this stuff used to look like before we decarboxylated? It looked like this. Diethylmelanate, CH2 double bond, CH2 double bond. We simply took our ester, we dumped it in aqueous acid, warmed it up a touch, it fizzed, and we got our product. So, what was our alkyl halide? We simply had a leaving group on our CH2 here, didn't we? So we could do an SN2. Had to have a leaving group. Let's pretend it was a bromine. Something like this. And of course, we need diethylmalonate. Our band ion attacked, bromine left. Here we are, dump it in acid, and we got our product. Now this is real organic chemistry, isn't it? This is what you heard about from everybody. Let's do this again. Start off with diethylmalonate and make this? You got to be kidding me. All right, well, we don't panic, do we? We look at it and say, find the carbons of the substituted acetic acid, right? Here's our carboxylic acid. This carbon here also came from the diethylmalonate. So the bonds we made are these two. We have this, it decarboxylated to give us this. All right. Here's our acetic acid carbons. That means that these are the two bonds that we made. Now, each of these carbons, this guy and this guy, had to have a leaving group on it, didn't it? Had to have a leaving group. Therefore, we can do something like this. CH2, 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 and bromines on the end. One, two, three, four. So 1,4-dibromo butane. Simply reacted with diethylmalonate. We attack once, we attack a second time, make our cyclic compound, hydrolyze the esters, decarboxylate, and by George, we've got it. All right, what follow are derivative versions of exam questions, okay? Because I know everybody's worried about this next exam. I'm so excited. I made this using a melodic ester synthesis. On the exam, you had a box. And all I wanted you to do was draw the structure of the alkyl halide. That's all you had to do. Okay, let's do the first one here. We identify carbons of our substituted acetic acid. This came from malonic ester, right? And everything else came from the alkyl halide. So our malonic ester anion reacted at this carbon. Here's the blue part that survived. This half down here Must have looked like that. And in the box, that's what you draw. Now isn't that fun and easy? Figure out the carbons of the acetic acid. This is the bond. Simply put the leaving group right there. Let's do this again. I made this using a melodic ester synthesis. Step one, identify the substituted acetic acid and the group of groups that have been attached to it. The blue part here is our acetic acid. We stuck on 2 methyl groups. The chemistry looks like this. The alpha carbon here attacked 2 bromomethanes. And in the box, you simply had to indicate bromomethane as a likely thing. Yep, I skipped one, sorry. So let's do this one. Identify the acetic acid. Break it at that point and put a leaving group on. There's our acetic acid portion, and all the rest of this was one simple alkyl halide. This carbon simply attacked this guy with a leaving group here, and that's your structure. Now these were all the really difficult ones. This is the one I like though. This was the easy one. Yeah. Yeah, just 2 moles or whatever. 2 moles. All right, again, this looks really odd, but identify the carbons of your acetic acid. And they're the blue guys here, aren't they? Carboxylic acid, and this is our carbon. The bonds we made are these. So really, all in the world you need is this thing with a leaving group on these 2 carbons. See, this is simple. This is going to attack twice. We need this as a dibromide to make our bicyclic product. All right, back to our bottom lines here. Enolates from diethylmalonate react with alcoholides to give substituted acetic acids. Never forget that. Well, we can do this same trick with all sorts of other things. We looked at acetoacetic esters a couple slides ago. Ethyl acetoacetate looks like this. Again, it's a beta diketone, very acidic hydrogens right here. Not surprisingly at all, we can enolize this just with ethanol to make our enolate anion. Now the enolate anion, just like we've done before, we can take this and use it as a nucleophile with an alkyl halide. Alpha carbon will attack, leaving group will leave, and we get this stuff. All right, well that's not surprising. That's the same chemistry we've done over and over. Let's take ethyl acetoacetate in its alkylated form and ask what happens if we dump this stuff in acid and hydrolyze the ester. We wind up with a beta keto acid. And just like a beta diacid, by George, this spontaneously decarboxylates. And we're left with this enol. What does this enol do? Reverts back to its ketone form. And by gosh, we've made a substituted methyl ketone. Here's the alkyl group we put on, methyl ketone, and another carbon. We've added a 3-carbon unit now to a carbon. Same chemistry as malonic ester, except instead of getting an acetic acid, we have a ketone. All right, starting with ethyl acetoacetate. Let's make this stuff. Step 1, it's a methyl ketone. That means it's a methyl group on one side of the ketone, right? So that's good. We know that in this reaction, the methyl group, the carbonyl, and this carbon all came from the ethyl acetoacetate. That's the bond that we make. All right, so this used to be attached here to the ester moiety before we decarboxylated. So the stuff before this, well, okay, I guess I did it backwards. Here we're going to attack on our bromopropane to get this. This is what this used to look like. This is the bond we just made. We acidify, lose CO2, and we're up there. Identify the 3 carbons of your methyl ketone. This is the bond we made. That gives you the alkyl halide, simple condensation reaction. Ethyl acetoacetate synthesis yields methyl ketones. Remember that. We add RX, decarboxylate, get a methyl ketone, another carbon, and an argon. All right, guys, there's one more biggie here. This is called the Carbonyl condensation. What if we took ethyl acetate, plain old ethyl acetate, and we dumped it into a strong base? We would make an enolate here, wouldn't we? We have lots of ethyl acetate sitting around, so this enolate anion can attack another carbonyl carbon. When it does, it makes this stuff. Here's the bond we just made. Here's our first ethyl acetate. Here's the second. Now we're going to protonate this. No, we're not. This is a tetrahedral intermediate, isn't it? Remember the tetrahedral intermediate from our chapter on acyl transfer. We have an oxyanion, and we have a good leading group. The oxyanion will collapse, and the leading group will go. What have we made? By George, we just made ethyl acetoacetate. That's how you make it. This is now a carbonyl. This is gone. Here's our methyl group from up here. Here's our CH2 in the middle. And here is our acetate. All right, so we made ethyl acetoacetate. What if we took, well, let's just go ahead and do another one first. Here I'm going to take a different ester, two of them. I'm going to condense these and make something. Again, this is the carbon that's going to be the carbanion. So, draw your enolate, draw the other ester, and all in the world you have to do now is make a bond from the alpha carbon to the carbonyl. Now this gives us our tetrahedral intermediate. It looks like that. Lots of arms and legs sticking out everywhere, right? But this is going to collapse. The oxyanion is going to become a carbonyl. The ethyl group is going to go. When that happens, we wind up with this strange looking stuff. Right? Now, again, the bond that we made here is this one right here. Make sure you understand that. This is 1 mole of ester. This is the other. We simply lost the ethoxy from this carbon. Now, I want to take this stuff and do something else with it. I'm going to dump it in aqueous acid. When I do that, this ester is going to hydrolyze, isn't it? This ester hydrolyzes. By George, we have a beta keto acid. What do beta keto acids do? Well, they decarboxylate. Now, this is going to decarboxylate, form an enol. When that collapses, what have we made? We've made a ketone. It's a symmetrical ketone. Each of these halves on both sides of a carbonyl. Lysin condensation. 2 moles of an ester. Link them together. Acidify, lose CO2. You get a symmetrical ketone. So our big 3 here. Diethylmalonate gives us substituted acetic acids. Acetoacetate gives us methyl ketones. And the Lysin condensation gives symmetrical ketones. That's all you have to remember. Let's do some very simple problems here. Start off with an ester and do a Lysin condensation, followed by acidification. Now on an exam or a quiz, you wouldn't have to draw intermediates, probably. You could simply look at this and say, okay, well this side chain is going to be symmetrical. So that's a nice simple way to remember it. Our first step, we're going to ionize one of them into an enolate. Anion is going to attack the other carbonyl. We will get a tetrahedral intermediate. When the tetrahedral intermediate collapses, we're going to lose methoxide and form this ester. That's step 1 in the reaction. Step 2, we're going to take this ester, hydrolyze it, make a beta keto acid out of it. We hydrolyze the ester, this decarboxylates, and by George, a symmetrical ketone. Once again, if you remember your 3 major points, you could have just simply looked at this and said, Lysin condensation, ketone, with a 3-carbon chain on both sides. Now our next one's a little trickier. Step 1, we're going to take malonyl nitrile, and we have it in strong base. This is going to be an enolate anion, and we're simply going to do an SN2 reaction. Okay. So in step 1, all we're doing is this. We're making the anion at the alpha carbon. Is what it actually looks like. But again, anion character here. This is going to attack our alkyl halide. Bromine's going to leave. And we would form this stuff. Simple alkylation. We can all do that. However, the second step on there was strong acid. Remember what happens to nitriles in strong acid? Nitrile is the same oxidation state as a carboxylic acid. Strong acid converts it to a malonic acid. That's a beta diacid. What do? They decarboxylate. And this is our product. This is just like the malonic acid synthesis. We have made a substituted acetic acid. Alanonitrile and malonic ester both give a substituted acetic acid. Here's the bond that we made. And finally, just to make it simple, do an aldol condensation on this guy. For an aldol, all we have to do is make the anion here. Here's our enolate, and it's going to attack the carbonyl of its friend. When it does, we make a bond from here to here and make a beta hydroxyaldehyde. Now we know we can take this and dump it into acid and make an alpha beta unsaturated, but I didn't show that on the slide. Simply base to give the beta hydroxyaldehyde. And again, here's the bond that we just made. Any questions?